In this video segment, we're going to be covering permutations. Now, permutations are arranging objects, sometimes it's numbers, sometimes it's an actual object like chairs or something, in a certain order. And it uses a mathematical concept called factorials. So we're going to take a look at what a factorial is, and then we're going to actually solve some sample problems that you can find in the Princeton Review book and see how you use factorials to solve a permutation problem. Okay, let's take a look now at some of the basics of permutations. Permutations, as I mentioned earlier, are taking objects and putting them in a certain order. And you want to know how many different ways you could arrange them. It may be, say, 6 chairs. And let's say each of those chairs has a different color seat, a blue seat, red seat, whatever. All of them are different, each one unique. What are all the different ways you could arrange them? Now, there's 2 things to look at: the objects that you're going to arrange, and, this is important, the amount of space that you have to arrange them in. Because this could be a Joe Boggs way to get you. And I'll show you what I mean in a moment. So let's take our example. We have 6 unique chairs, and we have 6 spaces we're going to put them in, okay? They're going to be side by side, 6 spaces. And we got these 6 unique chairs. How do you know mathematically how to do that? Well, it's very simple. It's called something that is a factorial. And the nomenclature for that is, in this case, I'll just use the 6 as our example here. They put an exclamation mark after it. That reads the factorial of 6. And the way they do that, it's a multiple product starting with 6, counting back to 1. So the factorial of 6 is 6 times 5 times 4 times 3 times 2 times 1. That's the factorial. So when you multiply that out, that's the answer to what the factorial of 6 is. So 6 times 5 is 30, 4 times 30 is 120, 3 times 2 is 6, 6 times 120 is going to be 0, 12, carry 1, 720. So there are 720 ways that we could arrange these chairs. But sometimes, let me just erase this, sometimes they will give you something and it won't match up. The space won't be as, you'll have more objects than you have space to put them in. For instance, let's just take the word math, for instance. There's 4 letters here. Now, the easy thing, if they gave it to you this way, they'd just give you 4 spaces and you do just like you did with the chairs. Those are each a unique object. But sometimes they'll give you 4 letters, but they'll only give you 2 spaces, let's say. And they want to know all of the combinations you could have with those letters in those 2 spaces. Now, the answer is not going to be just plain old factorial 4, which would be 4 times 3 times 2 times 1. What you have to do here is, and I probably should have done this with the 6 boxes to show you, you put each of the factorials under the box and you stop when there's no more boxes, when there's no more space. So the possible number of combinations you could have in pairs like this is 12. So this is basically what permutations are. Let's take a look now at some of the math examples straight out of your Princeton Review and see how we use this concept to solve problems. Let's take a look now at a problem that's basically a permutation problem, but it has some twists in it that I'll explain in a moment. This is a straight out of your Princeton Review samples, and it's got a number 15, which means it's perceived as being one of the more difficult problems. And in this case, I really have to agree because they've thrown everything but the kitchen sink at you with this one. Let's read it together and I'll show you what I mean. The American Ballet Repertory Company will choose 4 new corps members from its apprentice program. The apprentice program is made up of 6 women and 6 men. Now, if there are slots only, though, for 3 women and 1 man that can be chosen from that base of 6 women and 6 men, how many different groupings are possible? So let's first look at the permutations for the men, and then we'll look at the permutations for the women first, and then the men. We have 3 slots that are available, and we have 6 women. So that would be factorial 6. Now, since there's only 3 slots, we can only use the first 3 positions of that. And 6 times 5 is 30, times 4 equals 120. Now here's the problem. You don't want, this would be a Joe Boggs trap. Because it doesn't matter that what order we have, let's say that, let's call these 6 women A, B, C, D, E, and F, okay? And let's say that they decided after all this testing that they thought the best 3 women were A, B, C. So it doesn't matter what order they're in, they're still A, B, C. If I had C, A, B, or I had B, A, C, all we care about is who are the 3 people. So we've got a lot of duplication here if in this factorial 120. Now, how can we filter out all of the duplications? There's a little trick. You take the number of spaces that you're fitting this information into, and you take the factorial of that number. There's 3 spaces. The factorial of that number is 3 times 2 times 1. And that becomes our filter. We divide that into the total permutations. So 3 times 2 is 6. 6 into 120 equals 20. So that's how many permutations without duplications we can have for the women. How about the men? Well, it's an even worse situation there, although it's simple to figure out. We only have 1 slot. We got 6 men. So out of that factorial of 6 times 5 times 4 times 3 times 2 times 1, the only one you can use is the 6. So now, this is where we get into the other curve they've thrown at you is that now it's a probability problem, okay? So how many different groupings can we have with the 20 women and 6 men? And that is, since it's a woman and 3 women and a man, we'd multiply these, and 20 times 6 equals 120. And so your answer is that there would be 120 different groupings possible, and that's what you would grid in.